Hello, everybody. Today, we are in the last phase of our reproductive physiology. And in this subsequent 3 classes, we'll discuss about the pregnant uterus and the physiological changes which occurs during pregnancy, parturition, lactation, and we'll have a brief overview of the contraceptive devices. So today's lecture is on pregnancy. Let me share my screen and follow it carefully. And if you have any doubt, you can always WhatsApp me for clearing your doubts. So today's class, here I must acknowledge Dr. Shwasti Banerjee, who has helped me a lot in making this PowerPoint presentation. And the learning objective today will be, after this class, you'll be able to know about the mechanisms of fertilization, embedding of blastocysts, how it is being implanted in the dorsal wall of uterus, subsequently the formation of placenta and the several functions of placenta, including the placental hormones. And another interesting thing is the feto-placental unit. And lastly, fetus, as we all know, is a graft because it has the parental chromosomes within it, but still the graft is not rejected. So this is with this learning objective, let us progress to our class. Now, the steps of fertilization, as we all know, is that the sperm is deposited in the female reproductive organ, that is vagina. And now this sperm is attracted towards the ovum. And this is due to several chemoactive substances released from ovum. So it is called the chemo attraction of the sperm to ovum. And we all know the site of fertilization is the ampulla of the fallopian tube. Now, first what happens is there is adherence of sperm to the zona pellucida. Here you see that this is the ovum, and this is the perivitelline space with the plasma membrane of the ovum, and this is the jelly-like coat, or this is called the zona pellucida. So this is the zona pellucida, this is the ovum plasma membrane, and here is the here will be the perivitelline space. So in zona pellucida, we treat three types of ZP receptors. These are ZP receptors or Z receptors, ZP1, ZP2, and ZP3. And mostly ZP3 or sometimes ZP2 are involved in adhesion of the sperm to the zona pellucida. Now, once there is adhesion, then it undergoes the acrosomal reaction to penetrate the zona pellucida. And here, several enzymes like hyaluronidase, acrosin, they are being liberated, of which acrosin is most important, which is a trypsin-like protease for the penetration into the zona pellucida. Now, this fusion, subsequently, there is fusion of sperm with the membrane of the ovum, which requires the enzyme fertilin. Now, here we see that once there is attachment to the contact with the zona pellucida, there is the acrosomal reaction. First the adhesion, then the acrosomal reaction, and now penetrating or dissolving the zona pellucida. Now, after zona pellucida has been dissolved and it has reaches the membrane, this is called the vitelline membrane, we see that the acrosomal process is growing and it is coming in contact, not the entire sperm head, but the acrosomal process is ejected and it is coming in contact with a vitelline layer, and subsequently there is fusion of this sperm membrane with the plasma membrane of the ovum. So this is the fused plasma membrane of the sperm and the ovum, where we get the fusion of plasma membrane, and subsequently there is injection of the sperm nucleus into the cytoplasm of the ovum. Okay, and as soon as the sperm membrane fuses, two changes occur. One is that due to the calcium entry, there is transient change in the membrane polarity or the membrane potential, and that leads to the entry of calcium, which causes the cortical granules to degranulate and fuse with each other. This is called the cortical reaction, and this transient alteration in the potential of plasma membrane as well as the cortical reaction prevents polyspermy, that is entry of several sperm nucleus into the ovum. So it is only one sperm nucleus that is being pronucleus that is being injected into the ovum. And at the same time, as soon as this plasma membrane fuses, the third change which occurs is there is completion of the second meiotic division of the ovum nucleus, and the ovum pronucleus is formed, so that there is subsequent fusion of the two pronucleus. Now, thus, this is the ovum with the corona radiata and the zona pellucida. Now it is being penetrated by one of the sperm, and the sperm pronucleus is being injected. So two pronucleus now fuses. So each are haploid in nature. So now the diploid zygote is formed. Now, as soon as the zygote is formed, it starts mitotic division from 1 to 2, 2 to 4, 4 to 8. So it is the mitotic division until the 16th stage morula is formed. Now, this morula, we see that it enters into the uterine cavity, and this transition takes about 3 days. Now, after that, another 3 days, it floats into the uterine cavity when it changes from morula to blastocyst. That is, here it has differentiated into inner cell mass and the trophoectoderm, that is the syncytiotrophoblast and the cytotrophoblast, before it gets implanted into the uterine cavity. So here we see that a blastocyst being embedded. This is the blastocyst. So the 16th cell stage morula has now differentiated into the cytotrophoblast and the syncytiotrophoblast, and this inner cell mass is destined for formation of the embryo, whereas this trophoblastic mass is for the destined to form placenta. And this is the blastocele or the blastocyst cavity, which is now enlarging. So this now gets implanted into the dorsal wall of the uterus by 3 processes. That is, one is apposition, the other is adhesion, and finally the penetration or invasion. So in the apposition, we find that as they come near the suitable, favorable wall of the uterus, in the cavity of uterus, we see that the cell adhesion molecules like integrin and osteopontin, and along with the stromal fibronectin and the laminin, they help in the adhesion or attachment or apposition. And now there is the invasion, where we find that the syncytotrophoblast along with the cytotrophoblast both penetrates into the stromal cavity, and now the stromal cells, they change into rounded cells which are called the decidual cells. So there is decidualization of the stroma of the uterine wall, and at the same time there is invasion by the cytotrophoblast and syncytotrophoblast. And we see that how they are invading into the uterine vessels and even disrupting them to form a continuous if these are the chorionic villus, then this intervillus space is being having lacunae of blood vessels, and this blood vessel is coming from the maternal blood vessels. So here there will be growth of the fetal blood vessels, whereas villus space there is the maternal blood vessels. So the blood of the fetus is coming in contact with the maternal blood for exchange of nutrition, the respiratory gases, the excretion, and it also forms the placental barrier. Besides, there are several hormones which are also very, very important for the subsequent fetal growth. So now once it has been implanted, the implantation is complete. Invasion completes by 10 to 15 days. And we see that after this 12 to 15 days, the invasion, which was due to the enzyme matrix metalloprotease, is now being inhibited by the secretions of the embedded embryo, and that inhibits further invasion into the uterine wall. And now the blastocyst or the budding embryo is being tightly implanted into the uterine wall. So we find that now there is formation of placenta. So placenta formation is completed by about 6 to 8 weeks. So by about 6 weeks, we find that there is formation of embryo, beginning of formation and differentiation of embryo from the inner cell mass. And there is development of the umbilical vessels. And this umbilical vessels goes into the syncytio and cytotrophoblast, which has invaded into the uterine cavity. And this is all round. And this layer is called the chorion. Inner to chorion, there is amnion, which is with the amniotic fluid, which is cushioning and protecting and covering the budding embryo. And outside this amnion, there is the chorion with this chorionic villi, which is finger-like projections into the uterine wall, and the intervillus space or the interchorionic space is being filled up with a lacunae of blood coming from the maternal blood vessels. And here we see that the umbilical artery and vein, they are going into this chorionic villi. Now here one thing I must mention, that umbilical vein is actually carrying the nutrients and the oxygen rich blood to the fetus, and it is the umbilical artery which is carrying the less nutritional or more laden with the excretory and the carbon dioxide, which is returning to the placenta. Another two things which we can prominently see in this diagram. One is the yolk sac. This is responsible for providing nutrition to the embryo, and to some extent helps in exchange of respiratory gases as long as the placenta is in its making. And this is the allantois. It collects the liquid wastes. So this is responsible for the excretory function of placenta, which is subsequently taken over by the placenta. And this placenta, as we have said already, that develops completely by 6 to 8 weeks of gestation. So if there is any emergency of ovarectomy, that is removal of ovary in mother, because say after pregnancy, the ovarian carcinoma has been detected. It's a very virulent type of carcinoma, and so it requires immediate ovarectomy. Now, if both ovaries has to be removed, then it must be after this 6 to 8 weeks. If it occurs before 6 to 8 weeks, then there will be abortion, because before 6 weeks, placenta cannot fully function, and the endocrine function of placenta is being carried out by corpus luteum, mainly maintaining the blood levels of estrogen and progesterone. And so if ovary along with corpus luteum is removed, then definitely this pregnancy cannot persist. But after 6 weeks or after 8 weeks, if it is removed, then definitely the pregnancy can continue, because already placenta has taken over the endocrine function, and even the allantois, which is destined to form the urinary bladder, and the yolk sac, which merges with the gastrointestinal tract, this goes into its own embryonal development. So by this time, you must be knowing that the human have a haemochorial placenta. That is where the fetal blood is in direct contact with the maternal blood. This is the fetal tissue. It's connective tissue, the fetal blood, and this is the trophoblast, trophoectoderm. And now this is the lacunae of blood vessels in the intervillous, interchorionic space. So the fetal blood is coming almost in direct contact with few layers of placental barrier. It is in direct contact with the maternal blood, and so it is called a haemochorial placenta. Now coming to the functions of placenta, very, very important, the functions of placenta, without which the embryo cannot develop properly, cannot survive till parturition. So there are 5 important functions. There are several functions of placenta. 5 important functions narrated here. One is the nutrition, then the exchange of respiratory gases, then excretion, then the placental barrier, and finally the placenta as endocrine organ. Now the transport of respiratory gases. Now here we see that the oxygen, which in maternal artery you see is about the PO2, the partial pressure of oxygen is 100 millimeter of mercury. In intervillous space it is 30 to 35, and in umbilical vein it is as low as 30 millimeter of mercury. So the fetus has to do with very less amount of oxygen concentration. But if you see the hemoglobin saturation, you'll be delighted to see that in maternal artery with 100% PO2, the saturation is 97%, whereas in umbilical vein with 30 millimeter PO2, we see the saturation is 85.5 or 86%. Whereas in the intervillous space, it is much low, about 57 to 67%. Now, why this discrepancy? Why in umbilical vein, in spite of PO2 being so low, we have a good percentage saturation of hemoglobin? This is because this hemoglobin F has a very high affinity for oxygen. The dissociation is not that efficient, but affinity for uh, extracting oxygen from the maternal blood is quite high. And besides that, the hemoglobin level is quite increased in fetus, about 50% of that of the adult. So if adult has a hemoglobin percent of 15 gram percent, then a fetus may have as high as 22 to 23 gram percent. So this increased hemoglobin level definitely increases the efficiency of oxygen carrying capacity. And there is also relatively high cardiac output because the mass, body mass is very less per unit body mass. The cardiac output is relatively high, and this manages the oxygen demand of the body, and the percentage saturation is as high as 85%. In case of umbilical artery with a PO2 of 23, we can see the saturation is 65 to 66%. So this is very important to know that this oxygen saturation is quite high in the umbilical vein and artery. And another important thing is the double bore effect. We'll come to this. Just have a look on the carbon dioxide exchange. In carbon dioxide exchange, we see that in umbilical artery, the carbon dioxide is as high because artery is doing the function of vein. So it is as high as 48 millimeter of mercury, and in intervillous space, it is 43 millimeter of mercury. So they're the gradient of -5 millimeter of mercury. And so continuously, the high diffusing carbon dioxide diffuses from the umbilical artery to the intervillous space and thence to the maternal vein. So this carbon dioxide exchange is by pure diffusion, and in oxygen is also by diffusion, but here the affinity of hemoglobin F, the increased level of hemoglobin, and the relatively high cardiac output all maintains the oxygen saturation. Just having a look on the double Bohr effect. We all know the Bohr effect, that is the effect of carbon dioxide concentration on the oxygen dissociation, oxyhemoglobin dissociation curve. We see if the carbon dioxide concentration is more, the pH is low, and the oxygen dissociation curve shifts to the right. That is, the affinity of hemoglobin for the oxygen reduces, or the T state gets stabilized. Now, here we see the double Bohr effect. That is, in case of umbilical artery, we know that the carbon dioxide concentration is high, having a gradient of -5 millimeter of mercury. So carbon dioxide is given to the maternal intervillous space or the maternal blood. So here there is a relative lack of carbon dioxide or relative increase in pH. So this decrease in carbon dioxide concentration or a relative rise in pH leads to a shifting of the oxyhemoglobin dissociation curve of hemoglobin F. So it is in fetus towards the left. That is, the affinity for oxygen rises, and this affinity of this hemoglobin F for oxygen extracts more oxygen even at a partial pressure of 30 millimeter of mercury of oxygen, and the saturation is maintained more than 85%. On the other hand, because the carbon dioxide shifts into the maternal vein, and so hemoglobin F, so this is the maternal blood, we see that from the maternal artery, there is a shift towards the left in case of maternal vein. So there is more unloading of oxygen, and this helps in better extraction or better oxygen supply to the fetus. So this double pore effect helps to increase the fetal oxygenation in placenta. Now going to the excretion. We know that the excretion is mainly by diffusion of placental membrane to maternal blood, and as the excretory waste products like urea, uric acid, creatinine are more in the fetal blood than in the placental blood, so definitely there is continuous diffusion of these substances into the maternal blood. Third is the placental barrier. Now, placental barrier is membrane, selective membrane composed of several layers, as we have already seen. And this helps in diffusion of several substances, especially the nutritional elements like glucose, which is transported by facilitated diffusion. It is the amino acids which are carried by the secondary active transport. The vitamins, the minerals, the other essential elements are also being diffused along with the gases. And the larger molecules like LDL cholesterol or the hormones like insulin or the maternal antibodies that is very helpful for fetal protection. Only the IgG antibodies are being transported by receptor mediated endocytosis. The macromolecules like IgM, like large lipid or the larger protein molecules, the phosphates, the sulfates, these cannot be transported to the fetal barrier. But this placental barrier is known as the leakiest barrier because it is very poor in blocking the small chemicals. And one of the very important example is the phocomelia after the thalidomide injection. Thalidomide is taken by mothers for morning sickness, and it is seen that this thalidomide injection leads to the phocomelia. This is the seal limb, the baby with a seal-like limb. This is a very gross defect, birth defect, due to the chemical or the medicine thalidomide taken consumed by the mothers, which leads to the sealed limb in the fetus. Now coming to the placental hormones. Now this human chorionic gonadotrophin, HCG, then the chorionic somatomamotrophin, that is the HCS, human placental lactogen, and then the placental estrogen, progesterone, and there are relaxin, inhibin, several releasing hormones like TRH, CRH, ACTH, TSH, and then also opiomelanocortin, and several others. There are several placental hormones to list, neuropeptide Y. And here we see that this is the curve showing the placental hormone during pregnancy. You see that the estrogen progesterone starts from the very basal level at first week of pregnancy. From the second week, there is a gradual rise. Progesterone rises more faster than the estrogen, but we see that estrogen rises 30 times that of the normal level in normal adults, and progesterone on the other hand rises about 10 times more, but the peak is reached at about 36 to 40 weeks, and the measurable rise occurs after the first trimester. And the main hormone during this first trimester is the human chorionic gonadotrophin secreted from the syncytial trophoblast, reaches its peak at about 9 to 12 weeks, and it can be detected as early as 8 to 11 days. So in the second week of pregnancy only, it has started rising. So human chorionic gonadotrophin is very, very important. It is produced by syncytial trophoblast, glycoprotein in nature, and pregnancy specific is beta HCG. Beta subunit of HCG is very, very important. And it is present in non-pregnant blood, only 10 units per liter. But if it's more than 25 units per liter, then only the pregnancy is being confirmed. And the pregnancy test, the CART test, depends on this level of HCG. As we said, it is detected as early as 8 to 11 days after conception or after fertilization. And we see that the HCG rise causes morning sickness. And HCG is a very important hormone. Now, the functions of HCG to speak about, we already told you that it maintains the health of corpus luteum because it has affinity for LH receptors, very similar to the LH, the alpha subunit. And so it has a peak towards the first trimester and decline the function as placenta takes up its function. Now, it also helps in trophoblastic growth and development of placenta. That is also a very important function. Now, stimulates several hormone production, especially the testosterone and DHEA. If you remember the sex differentiation, that you know that this early rise of this testosterone and DHEA is very important for sex differentiation. And along with progesterone, HCG contributes to the uterine quiescence. That is, it inhibits the oxytocin sensitivity, downregulates the oxytocin receptors so that the uterus remains quiet and there is no chances of early abortion. Now then, placental estrogen secreted from syncytial trophoblast, as we all know, and it is about 30 times the normal level. Now, in placental estrogen, the type is E3 estriol, not the estradiol E2 from ovaries. That is a very important differentiation. And this DHEAs and 16 DHEAs, these are the precursors for estriol E3. And this is 80% derived from the fetal adrenal cortex. Now we'll come to these details in the feto-placental unit. Now the function of placental estrogen are several. To name a few: enlargement of uterus, proliferation of ducts, not the alveoli or the lobules. That is the function of progesterone. Now the development of external genitalias and relaxation of pelvic ligament to accommodate the pregnant uterus with its volume. It is very, very important, the relaxation of the pelvic ligaments. Progesterone also secreted from syncytial trophoblasts, very high during the late trimester, and it is converted to cortisol and androsterone by placenta. Progesterone is a precursor of that also. Now, this priming of endometrium, it's a progestational hormone. So it helps in priming the uterus to receive and maintain the pregnancy. So priming of endometrium and decrease the contractility of uterus along with HCG, so it prevents abortion and helps in development of lobules and alveoli of breast, lobules and alveoli, and the duct by the estrogen. And also, it helps in inhibiting the immune response. As we have said, that fetal graft, though is a foreign body, it avoids rejection. And progesterone is one of the very important hormone to prevent the graft rejection. And it stimulates the maternal hyperventilation. Maternal alveolar ventilation is being increased by progesterone. That is also very important because the diaphragm rises up and the abdomen swells up. So the ventilation has to be increased to get rid of the carbon dioxide, which is produced in more amount. Then human chorionic somatomammotrophine, HCS. This hormone is now said to include the placental lactogen, the chorionic growth hormone, and the prolactin. All encompassed together is the human chorionic somatomammotrophine. This is also secreted from syncytial trophoblasts, so it helps in growth and development, as well as some milk forming activity, breaks down the lipids. It inhibits the insulin action so that there is hyperglycemia and glucose can be transferred to the fetus. Now coming to the pregnancy tests, mainly based on the beta subunit of HCG, level of beta subunit of HCG is very important for the pregnancy tests. Now, the urine dipstick test or the card test, which is very common nowadays to detect pregnancy at home, that is actually a chromatographic immunoassay. Chromatographic immunoassay giving the color. The change of color will give you the test. And the commonest are now the ELISA, enzyme linked immunosorbent assay, or the radioimmunoassay. So these immunoassays are commonly used nowadays to detect pregnancy. Yes, and in the ELISA test, we see that mostly the monoclonal antibody against the HCG is being used, so that it is very specific for beta subunit and ensure there is no cross reaction with the LH component. Now, to name few obsolete tests nowadays, one is the biological test like Asim-John-Deck test. There are several. We have to mug up at least 5 to 6 such tests, where we actually used to take the maternal urine and inject the urine into the host like rabbit or frog or rat. And this rat or rabbit should be immature one. That is, they are not ovulating or they are not going into the estrus. Now, after injecting HCG, if the maternal urine, if it contains HCG, then we find that subsequently, if we sacrifice the animal and see the ovary, we see the ovaries are enlarged, and there are some bleeding points, that is the ovulation in the ovary, and signs of follicular maturation. So, but this is a very cruelty to sacrifice animal just to know about the pregnancy. And hemagglutination test is like that of the blood grouping. That is, the HCG antibodies are being tested with maternal urine, and if there is agglutination, then the pregnancy test is positive. Pregnancy test is very important for detection. And now for confirmatory tests, we go for the blood estimation of the beta subunit of HCG. Definitely we can assay and know the level, so that we are confirmed that it is the pregnancy and nothing else. Because false positive cases are noted in ectopic pregnancy if the pregnancy occurs in the tube itself. So the tube will burst, the pregnancy never survives. High datiform mole, where a large number of such chorionic villi are formed due to some improper pregnancy. Only the chorions, and there is no fetus as such, but they are producing HCG, this in situ trophoblast, so it comes positive, and also many of the germ cell tumors. So we must be very sure about the pregnancy. Now we have come to an interesting phase, the feto-placental unit. Now, so long we have known that the fetus is dependent on mother for its nutrition, respiratory gaseous exchange, excretion, even protections from the placental barrier. But in some cases, we see that the mother also have a joint effort. That is, placenta and mother are interdependent, and they act as a functional unit, have a joint effort in steroid biosynthesis, because maintaining the hormone level is very, very important. And this leads to the concept of feto-placental-maternal unit, or it is simply said as feto-placental unit. Now, we all know that fetal adrenal gland lacks 3-beta hydroxysteroid dehydrogenase. In short form, it is 3-beta HSD. And so it cannot convert pregnenolone into progesterone or the estrogen precursors into estrogen. Now, this has a safety profile as well, because if it continuously produces progesterone from pregnenolone, then definitely it will be under the huge load of exposure to progesterone and estrogen, and that is detrimental for it. And on the other hand, this DHEA, which is produced in the fetus, it is readily conjugated with a sulfate from DHEAS, because DHEA, if it is in very high concentration, may cause masculinization, mainly in the female fetus. So we see that the deficiency of the enzymes have also some meaning. On the other hand, if we look at placenta, the maternal side, we see it lacks 17 alpha hydroxylase, 17 alpha hydroxylase, and 1720 desmolase. These two enzymes are present in abundant in the fetus, so that it can produce enough of DHEA from pregnenolone, which is the precursor of mainly the estriol, E3, and also from here we can produce the estrone and the estradiol. So if you see here that the LDL cholesterol, it goes into the placenta from maternal side, but enough of LDL cholesterol for such huge hormone synthesis is not available. It has to come from the fetal adrenal. Now, this LDL cholesterol is converted into pregnenolone in the placenta. It has the side chain cleavage enzymes, and this pregnenolone gets transferred into the fetus to form pregnenolone, conjugated to form pregnenolone sulfate. Now, this pregnenolone sulfate can also be formed from the LDL cholesterol. Now, this pregnenolone can not be converted into progesterone in the fetus because there is no beta HSD, that is the hydroxysteroid dehydrogenase. So there is no risk of fetus being exposed to excess of progesterone. At the same time, they have enough of 17 alpha hydroxylase and 1720 desmolase, which are deficient in placenta. So here they are converting pregnenolone sulfate to DHEA sulfate, dihydroxyepiandrosterone sulfate. And in fetal, this occurs in the adrenal cortex. And this DHEA is circulated to fetal liver, where by 16 alpha hydroxylase, it is converted into 16 alpha hydroxylase DHEAs. This 16 alpha hydroxylase is also not present in adequate amount in the placenta. So what happens, there is the precursor of 17 alpha hydroxylase DHEAs. This is the precursor for formation of estriol, that is the E3, by the aromatase enzyme present in enough amount. And before that, it should be by the sulfatase enzyme, it should be desulfated. And then the estriol goes into the maternal blood. On the other hand, this DHEA sulfate, if it's not converted into 16-hydroxy, this dihydroxyepiandrosterone bisulfatase enzyme converts into DHEA, and that is converted into estradiol by the aromatase of 17-beta-HSD, which is again not present in the fetus. And so this estradiol and the interconversion of estrone and estradiol, that is E2 and E1, this continues. So there is enough formation of estrone and estradiol also because of presence of 17-beta-HSD in the maternal blood as well as in the placenta. So the precursor for this estrogen, 3-estrogen, that is DHEA, is produced in enough amount in the fetal adrenal and fetal liver because the placenta is lacking 17 alpha hydroxylase, 1720 desmolase, and 16 alpha hydroxylase. So we find that enough of estrogen is being produced, and this level of estriol is often seen, often being checked in the to see the fetal health. If estriol is not produced in adequate amount, we know that the fetal health is not adequately maintained. And similarly, from DHEAs, the progesterone, enough of progesterone is formed, because that is very, very important. This pregnenolone, it converts into enough of progesterone by beta HASD, and that is being produced in the placenta and goes into the maternal blood. So thus, to summarize, we see that both the placenta as well as the fetal adrenal, they lack certain enzymes and is interdependent on each other for the steroid biosynthesis. And the steroid hormones, that is the estrogen and progesterone, is very, very important for maintaining the pregnancy, and that can be produced by the unitary function, the interdependent function, or the joint effort of the placenta as well as the fetal adrenal and liver. Now, coming out to our last leg, some physiological changes in pregnancy. In blood chemistry, we see that the blood cells are increased in number. There is increase in clotting factor, so the viscosity increases. So in pregnancy, we see that ESR increases. At the same time, fibrinolytic activity also increases to maintain a balance. And in spite of large blood cells, RBCs being formed, the hemoglobin cannot keep pace. And if there is no iron supplementation, then often iron deficiency or anemia occurs in the mother. Now, then for the cardiovascular system, we see that there is increase in heart rate as well as increase in cardiac output because of increase in the stroke volume. So this ultimately should lead to an increase in the mean arterial pressure, but mean arterial pressure does not rise that much till late, because we find there is vasodilatation, mainly by the effect of progesterone, peripheral vasodilatation. To coming to cardiac output, we see that total cardiac output increases by 45% throughout the pregnancy, of which 33% increase occurs in the first trimester. And in the respiratory system, we have already seen that there is alveolar hyperventilation because of the effect of progesterone, and diaphragm moves superiorly, so the functional reserved capacity is decreased. But the tidal capacity, tidal volume, it always increases. And due to the increased ventilation, we see that although the carbon dioxide is produced more in the maternal body, but there is not carbon dioxide accumulation. Rather, there is mild respiratory alkalosis due to the increased washout of carbon dioxide. Now, in gastrointestinal system, nausea, vomiting, and this morning sickness is related to the high level of HCG. So it occurs in first trimester, and heartburn, acidity at later phases when the stomach, the entire abdomen gets distended, stomach has its less capacity. And in the general changes, there are mood changes and increased nutritional demand. Three things you have to remember in increased nutritional demand. One is the protein. At least 30 gram more protein should be taken per day, and iron, the daily requirement from 1.5 milligram per day raises to about 7 milligram per day, the absorption rate. So we know that how iron turnover is increased. And another is folic acid, because new cells are growing in enormous rate. So 400 to 800 microgram per day, folic acid should be supplemented in a pregnant woman. And last thing I wanted to tell you is about the in the pregnancy changes, that about the total the 11 to 16 kg rise in maternal weight, it is about 3.3 kg which rises due to the fetus, and about 1.5 kg due to the placental membrane and the embryonic fluid. 2 kg for breast, and less 3 to 5 kgs is for the adipose tissue and the interstitial fluid. Now, a few words about IVF, in vitro fertilization, which is an assisted reproductive technology. There are several other assisted reproductive technology, ICSI, GIFT, and IVF is one of them, where the oocyte is collected, the sperm is being retrieved, they are being washed, processed in the laboratory in vitro, and they are fertilized in vitro. This fertilization rate is also very high, about 80%. But what happens is that when it is implanted into the fetus, then into the mother, then this implantation and the subsequent development becomes a risk. So only 8 to 15% success rate is for IVF once the embryo is transferred. That is where there is a failure. And but still now it is gradually improving from Subhash Mukherjee to nowadays. It is the Boidonath Chakraborty and Dr. Sudarshan Ghosh-Sidar. They are doing a great job on this IVF and putting a smile to the infertile couple. Now, the last one is about the fetal graft. We know that the mother and fetal are genetically different for the paternal genetic material, but why fetus is not rejected? That is because of the immune tolerance. So what is the immunosuppressive mechanism for which the fetus is not rejected? First and foremost is that the early embryo do not express the MHC class 1 and class 2 on the placental layer in contact with the maternal tissue. So maternal tissue cannot identify them as a foreign agent. And the cytokines that enhance this major histocompatibility cell expression does not have any effect on placental cells. So MHC expression remains suppressed, number one. Number two, T cells are prevented to function on placenta because of fast ligand. Fast ligand on the surface of placenta binds with these T cells and they undergo apoptosis. So we find that as the fast ligand is more on the surface of the placenta, we see that they undergo apoptosis and are prevented from acting on the placenta. And the third point is the expression of HLA-G molecules on cytotrophoblast. This immunoleukocytic antigen G acts as the at the maternal fetal interface. Thus, no antibody formation is being allowed, and this all prevents the fetus rejection. So there is prevention of expression of MHCs as there are no cytokines. Then due to the presence of fast ligand on the surface of placenta, the T cells cannot undergoes early apoptosis, so cannot destroy the graft, and HLA-G molecules at the maternal fetal interface prevents the antibody formation and also prevents the rejection. Thus, fetus being a graft is not rejected. There is cross immune tolerance. So thank you, everybody. Thank you for your patience. Have a good day.